So in this session, we'll be now covering conditional probabilities. Conditional probability. Okay, this is the most important topic in probability. Now you are done with basic probability, you know a lot of stuff about basics of probability, and if given questions, you can model problems. You can then compute the probability of an event if you are given some event to compute the probability of. Now the question is, in the real world, if you see the example that, if you remember, that I gave in the first session was, if somebody has a COVID and then test accuracy was this much, and then I told you to calculate something. So here you had some prior belief, you had some information. So that's what this conditional probability is all about. So this concept is basically in two folds. If you see it, there are two meanings associated with it. So the first thing is, we're interested in calculating probabilities when some partial information is given. When some information is given and we want to calculate based on that information some other probability. If you take the example of that COVID case, I was saying the prior probability was given to us. We were given information like this: in 1,000 patients, one patient is affected by COVID. So this was our prior information. Then we said that if a test is performed on a patient, what's the probability that test is showing that it is COVID positive? This is what is given to us. Okay, and now we want to compute the probability: is he actually COVID positive or something like that. So now some partial information is given. So I said this conditional probability is twofold. So the first fold is if you are given some partial information. So based on that partial information, you want to analyze the situation and you want to get some probability. Okay. Second is that when there is no partial information available. Okay. But you have some prior belief, you have something. Okay, and then you want to compute these things. The first thing is prior information will be given. Second thing will be that you have some partial information in the first setup. In the second, you have no partial information, but there is some condition which is given to you. For that, you want to compute this desired probability. Okay, how does it happen? Like, let's take an example of a die. This is a really important concept. I cannot emphasize it enough. If you know this condition of probability, more or less you will know 60-70% of probability. Okay, so let's take an example. So if I take an example of a fair die, I take an example of fair die. So the output in that fair die can be, the sample space is 1 to 6. Now if you assign probability, if each event or every event in this, every elementary event is equally likely, so I can assign the probability 1 by 6 to each event. Okay, so here I can enumerate these events. So this is 1, 2, 3, 4, 5 and 6. So for each of these I can assign probability 1 by 6 based on the frequentist approach, or based on number of events that are in sample space, and then I'm dividing it by that. So now what I'm saying is, if somebody said that if a person rolled die and he got an even number, okay, now some event happened. Okay, the event is that event is getting an even number. Event is getting an even number, getting an even number. So what even number can be there? 2, 4 and 6. These are the even numbers. So now if somebody tells me what is the probability of getting a 2, so he is giving me information. So probability of getting 2, when an even number showed up. Now you see that I have been given partial information. This is my partial information. Some experiment was done and they are saying that even number has appeared. Now you know that there can be only three possibilities: 2, 4 or 6. These are three possibilities of even numbers. Now I want to compute the probability of getting a 2. So I think everybody of you will agree you can compute this probability really easily. So what is the answer for this? Can somebody tell what is the answer for this?
1 by 3.
This is 1 by 3. Okay. Now we'll try to formalize this thing. Now we'll try to see mathematically how did we arrive at 1 by 3. Because intuitively it seems really easy to compute this probability 1 by 3. The first reasoning that is there is, now it can be seen the first approach that I like to call it approach 1. So how we see this? So now our whole sample space is this much. So we reduced our sample space. So we reduced the sample space. Okay, when we reduce the sample, then we reassign the probabilities. That is what we did intuitively. I think Rian said the answer 1 by 3. So why did he said 1 by 3? So he said, okay, this event E has happened. So that means 2, 4 or 6 will happen. Now as in the initial stage, we assumed that each event is equally likely. So the approach one is that I'm saying that if you are given that some event has happened, so what you are saying is that if that event has happened, now I will make that event as my sample space. This is now new sample space, and then I'll reassign the probabilities. The point in that was in the first case, if you see in here, we had this each event was equally likely, so we assigned probability based on that 1 by 6, 1 by 6, and we can also assume the similar thing over here because nothing has happened because events still remain those events. Again, you can reassign the probabilities. Now you can give each of this as 1 by 3 probability. That's why we gave the probability of 1 by 3 and 1 by 3. Is the approach one clear? How did we see it? So we just reassigned the probability. So whatever the sample space was initially, so there we had some probability. Then when some event happened, we reduced the our whole sample space to that to that event which happened. So what is the one assumption that we have here? The assumption that we have here is whatever event has happened, so it has some intersection with the event that is the probability of the probability of thing is being asked. So if we're asked, let's suppose probability of 2, let's call this event f. So this is probability of 2, probability of getting 2. Okay, and then we had this e, probability of even number, not even the probability by setting, getting 2 and getting an even number, getting an even number. So probability of f now means probability of getting 2, and probability of e now means getting an even number, probability of getting an even number. So there should be some intersection. So probability of e intersection f, it should be some number, it should be greater than 0, I'll say. If it is greater equal to 0, that means there is no intersection in that. You can still apply the apply this conditional probability on that, but still here taking the simplest case is that we assume that there is some intersection. These are not mutually exclusive event though, so these are not disjoint sets, so there is some intersection again. So now given this experiment, given such an experiment, so we can see that if you are given an experiment, from an experiment an event happened, you will make that sample space and compute the probability based on that. So how do you write it now? So probability of event e given that f has happened, this is written like this. So in mathematical notation, this is probability of e given f occurred. So here the experiment f, the experiment was done and f has already been seen, f has happened already. So this is what we write, the probability of e given that or conditioned that f has occurred. This is what we write. Now we can again see. So we are rolling 2 dice. So let's again experiment. So we are rolling 2 dice now. Rolling 2 dice. So in the rolling of 2 dice, you know that there are 36 possible combinations. So it can be 1 1 1 2 1 to 6. Similarly, it can be 6 1 6 2 till 6 6. So this is what we can get from rolling of 2 dice. Now let's suppose on the first die we got 3. On the first die we got 3. Okay, now this is our experiment E. So if you write the sample space of E, that will be 3 comma 1, 3 comma 2 till 3 comma 6. Okay, so this is our probability now. So this is our new sample space. So this is our event. So this has already occurred. So if now f is let's suppose sum of the number is 4, sum of numbers on 2 dice is 4. Now I am asking you, what is the probability that some numbers is 4 given that e has happened? So how will you do it? The first approach, keep that in mind. So initially if you see that each of this has 1 by 36 probability, so each of the event. So I told you 2 approaches. The first thing is that we'll make a box like this for thinking purposes. So this is how many boxes there which I made? 2 3 4 5 and 6. Let's make it like this, 6. And this is one more. Okay, this is the 1 2 3 4 5 and 6. 1 2 3 4 5 and 6. So the first thing is we got 3 on the first die. So this is our first die here, this is our first die, and this is our second die. So we got 3 on our first die, that's this. So we got whole of this. So this is our E, whichever I colored with the red. Okay, 3 1 3 2 3 3 3 4. And then second is sum of the 2 dice is 4. So how can I see it? Sum of 2 dice is 4. So it is this 2 2, this is there. Okay, this 3 1 is there. Okay, and what else is there? Sum is 4, then 1 3 is also there. So 1 1 3 is something like this. Okay, and what else? 1 3. So in our sum of two numbers is 4, we have 3 1, we have 1 3, and then we have 2 2. So these are the elementary events that we have. You saw we have only three elements, I think. So if somebody asks me to compute this probability, so how will I compute from this? So how will I compute? By using approach 1. So what's the probability, Rian?
Yes, sir.
So what is the probability? Probability of F given that E has happened. Are you able to understand the question? The question is, we are having two dice, and in that we are rolling these two dice. We'll get some number. The sample space that we have is 1 comma 1, 1 comma 2 till 1 comma 6, then 2 comma 2 comma 1, 2 comma 3 till 2 comma 6, and at the end 6 comma 6. So then possible outcomes were 36. That's why in the initial run when we had two dice, each of the elementary event has a probability of 1 by 36. Now what I said is there are two experiments. The first experiment is E. E means the first die that we rolled, we got a 3 on that die. So the for the E, the possible sample space is 3 1, 3 2 till 3 6. Now the second event that I said is F. So F is sum of the numbers on the two dice is 4. So for that, this is the sample space. 3 1 1 3
Sir,
2
1
2.
1 by 1 3
3
6.
1 1 3 2 2. So now question
So
asked is
now question asked is
probability of F given E. Probability of getting a sum of two dice is 4, given that on the first die we got a 3.
1 by 6.
1 by?
6.
This is 1 3 3 1. I think this is not there. Wait, wait, wait. This is one, and this is one more. One. This is 1 3. This is my 3 and 1. These three, 1 2 and 3. This over here is my event F. This red over here, this is my event E. The answer you said, Rian said the answer of 1 by
1 by 6.
1 by 6. So how did you compute it?
Sir, I just saw that since 3 has already occurred, there is only one way that the
There
sum
is
can
only
be
one way.
4.
Basically,
There is only one way.
you
Basically,
reassign the
you
probability. Okay, you reassign the probabilities. How did you reassign the probability? Initially we had 1 by 36 in this. Now we have only 6 events here. So each event here is of probability 1 by 6. So there is only one event that's matching the criteria. That is this 3 comma 1. So this is the only one which is matching the criteria. Now you can see it in the other light. Now I would go with the other approach also. So probability of F given E. So now we won't reassign the probability. What we will do, we will play with the old probabilities that we have. So what we will see is, so we'll see the number of elements that are in F. If you see it over here, you see how many number of elements are there in here. Okay, how many number of elements. So if you see there are three elements, 1 2 and 3. So number of elements in F, I'll see. I'll see this. So this approach, I'll call it approach 2. Approach approach 2. So I'm not reassigning probabilities now. So what I'm trying to do is, I'm trying to see that how many number of elements that are fitting this criteria out of how many out of how many numbers. So if you see in here, so you see that there is one overlap. So this is the overlap that we have in here. So this is the overlap. So what I can see is, I'm writing, okay, what is the probability of the overlap? So I'll write probability of the overlap, probability of E intersection F. Okay, this is the overlap. So I'll write its probability. What is the probability of getting an overlap? Then to normalize it, so I'll write the probability of whole of this divided by probability of whole of this, probability of event E. Okay, and that is this. So if you see it over here, so I did not recompute the probability. Now I did not reassign the thing. So I said compute the probability. Compute basically I can even without the probabilities I can say compute the number of elements that are there in. So even before this probability, I would like to show you compute the number of elements that are in the intersection of these two. What is the number of elements that are in the intersection of E and F divided by the number of elements in F. Okay, so how many elements were in the intersection? That was this one element. Okay, this was one element, and divided by how many number of elements were in the F? That was 6. Okay, this is how we got this. So this is our approach 2. Our approach 2 said that compute the number of elements that are common. So as you said in the approach first, you just recompute the probabilities. But here you don't need to even care about the recomputing probability. You will just see how many number of elements are in the intersection of both of these. Okay, and then see in the how many number of the elements are there for the event which already happened. So this is number of elements that are in intersection of E and F, and number of elements in F. Now I can divide it with the sample space. I can say that I can write it like this: number of elements divided number of elements in sample space divided by number of elements in F divided by number of elements in sample space. So this at the top upper portion I'll call it probability of E intersection F divided by this I'll call it probability of F. How many of you understood? This is approach third. So I'm saying that if you have to compute the probability of F given E, so the first thing is you can just take the sample space and reassign the probability. So one thing to do it mathematically is just check how many elements are there in the overlap. Okay, now this event has happened. If you see, this red event has happened. The red event has already happened. If red event has happened, now there is only one overlap. This is the overlap element. It's one. So I said number of elements in the intersection of these two events. The event which we are computing the probability of, and the event which already happened. See the number of the common number of elements there are. Okay. Then divide it by the number of elements that are in F, because now you know that this has happened. This whole red portion has happened. So this is the formula that we got. So in our case, we said that number of elements in E intersection F is 1, and number of elements in F, that is 6. So what I did, I just did a mathematical trick. I said divide numerator and denominator by n of s, by total number of elements in the sample space. So by the frequentist approach, or by the if we have discrete probability, so there you can directly write it probability of E intersection F divided by probability of F. So this portion over here is probability of E intersection F, and this probability over here is probability of F. So probability of F intersection E, this is equal to probability of E intersection F divided by probability of F. This is the formula that you will see in the books. So how many of you understood? This is not just a theorem or something. This is the definition. So how do we arrive at this? Did you saw how did we arrive at this? How many of you understood this? So again, to reiterate, if you see, so we had the conditional probabilities applied if you had been given some information, some partial information. So I said that let's suppose we take a die, we take two dice and we're rolling them, and somebody said is that on the first die we got a number 3 on that. Then somebody asked us, let's call this event E. The sum of numbers is this is event E. This is event E that the first on the first day we got 3, and the second event is F. Sum of numbers that we got on both the dice is 4. And somebody asks us that E has happened. That means he wants us to compute the probability of the F given E. Probability of getting sum of numbers as 4, given that the first die had 3 on it. So we just constructed one approach. The first approach was consider the whole F as our new sample space. Now you know that this E has happened. Sorry. So consider this E as our new sample space, because you know that this has happened. Now in the initial we had 1 by 36 probability for each event. Now all the other events, so all the others, they got probability 0. All of these got probability 0. For all of this, the probability remained 1 by 6, because we have to recompute the thing, because some of the probability should be 1. So for all the things we got probability as 0. So we had 1 comma 1, 1 comma 2, 1 comma 3 till 1 comma 6, and then 2 comma 1 and things like that. This is 3 comma 2 till 3 comma 6. This is 6 comma 6. This is what we had. So I said that when you know that this thing has happened, okay, 3 comma 1 has happened. So I'm saying that here each of these became 0. So for all the things, for all the other events, the probability now became 0. Now you still know that you have to respect the axiom of probability. You have to respect that summation of probability of these events should be equal to 1. So now you have to recompute the probability for these, because you know that this happened. So that's why we reassign the probabilities. How? Because now there are 6 elements in here. In order to respect this probability axiom, in order to say that the sum of probabilities is 1, you will recompute the probability. You will say that each of this will get probability 1 by 6, 1 by 6, and 1 by 6. Okay. Now you see that this has happened. This has already happened. Now if somebody asks what's the probability that this E has happened, and we want to compute the probability of F, that is the number should add to 4. So there is only one event which gives us the summation 4, that is 3 comma 1. So this is the event. So we know that its probability is 1 by 6 because that we pre-computed. Okay, that is the approach one when we reassign the probability. Again, I said there is a second way of looking at this problem. The second way is that how you can look at this problem is you can see what is the intersection, how many number of elements are present in both of this f and e. Okay, and then see, because you have to normalize this event already happened, make it because this is the new sample space. We said that probability of f given e, check the number of elements that are there in intersection of these two and then divide it by the number of f. Okay, and from this we also compute that probability of f divided by e even without compare number. If you just know the probability, you can just see probability of f intersection e divided by probability of f. This is what we can compute. So even from this we can again see it like this. So probability of f given e is equal to probability of e intersection f, or probability of f intersection e divided by probability of f divided by probability of, this is e, sorry, whatever has happened. So this is our event for which we want to compute probability, and this is our event that has happened, and this is the intersection between those events. So if I have probability of e given f, so this denominator will get changed. Now f has happened. Okay, rest will remain same. Now we'll go and solve some problems so that we'll have a proper understanding of this. The first problem that I'll tell you is a problem. It goes like this. So we have we are in a classroom. A student is taking an exam. Okay, so exam limit is 1 hour. So exam limit is 1 hour. So this is the exam. The student is taking the exam. So the exam can grow from 0 to 1 hour. It's up to student. When does he want to quit the examination? When does he finish the paper? He'll sort of give the answer paper to the examiner, and he's done with the exam. So now question goes like this. So you have, for example, the probability that a student will finish the exam in x hours. So student will finish exam in x hours is x by 2. This is the probability given to you. So probability that student will finish the exam in x hours is equal to x by 2. This is given to you. Okay, so x here lies between 0 to 1. So the maximum time he can give the exam to is 1 hour, or he can be absent, that is he will not give the exam at all. So now you have a given situation. So what is given to you? Given to you is that at 0.75 hours, so at the time 0.75, that is he has spent 45 minutes in the exam, he is still writing. So he is still writing his question answer paper. So what is the probability, what is the probability that student will use full 1 hour? Okay, this is the question that is given to you. Again, I'll reiterate the question. The question goes like this. A student is taking an 1 hour exam, and suppose the probability the student will finish exam in x hours, that is x by 2. Okay, and x should lie between 0 to 1. Now you are given that student is still writing the exam at 0.7 hours. So you have the question you're asked is, what is the probability that student will use the full 1 hour? The problem goes like this now. So now if you again see the problem, first we'll try to mathematically model the problem, getting it in the math world. Let's suppose we'll say that L of x, this denotes the event that student finishes the exam in less than x hours. So this is student finishes his or her exam in less than x hours. This is the first variable I introduced, L of x. So what I can write is, then I can again introduce one more variable, f. F means he'll utilize the full hour. Student will use the full hour. Student uses full hour. Student uses full 1 hour. This is the most important thing. First you will have to assign the variables. Okay, then you can solve the problem. Now I have to compute probability of f given that probability of 0.75 complement. Who understood this? This is what I have to compute. If you understood the question, you should be able to compute, you should be able to understand this. So the question asks me, what is the probability that student will use the full hour? Because I know that given that student was seen at 0.75 hours. Now I am saying that f 0.75 hours means student finishes in less than 0.75 hours, but its complement is he'll take more than 0.75 hours. This is the complement. Okay, given f means student will use full hour. Who understood this? Tell me this. Who understood this portion? I cannot see the screen. You have to speak.
Yes, sir.
Okay, you understood this. So now I have to compute the probability of. I have to compute this. I have to compute probability of f. I have to compute probability of f intersection L 0.75 complement. These are the two things I have to compute. Now, if I have to compute probability of f, how will I compute it? So probability of f means student will utilize the full hour. So this means probability of student will. This L of 1 means probability that student will finish within 1 hour. He'll finish less than 1 hour. So taking its complement says that student will fully utilize the 1 hour. Okay. Now this is equal to 1 minus probability of L1. So now you know that the probability given is this is 0.5, because you know that L1 is x by 2, that is 1 by 2. So this is 1 minus 1 by 2, this is 0.5. How many of you understood this? The question that he was asked, what is the probability that student will use full hour given the information given? He was seen at this 0.75. He was seen that he is still writing at exam at 0.575 hours. So the first thing I said is I introduced two variables. I said let L of x denotes that student will take less than x hours. Okay, you know that x here ranges from 0 to 1. Okay, so then I said f is student uses full hour. So now I had to compute this given f 0.75 complement, as 0.75 means that student will use less than or equal to less than 0.75. So but now we have seen a student writing at 0.75, so that means we'll take complement of the event. So that's what I written given that this, and then student will use the full hour. So now I know that if I have to compute this pf given f 0.75 complement, I have to compute p of f. I have to compute p of f intersection L 0.75 C. So now I said how to compute this p of f. P of f can be computed like this. So p of f means student will take full hour. So I am saying student will take full hour. I'll write it like this: probability that student will take less than 1 hour. Its complement. That means student will take full hour. If it's less than 1 hour, so if you exceed it, so it means it will be greater than or equal to 1 hour. But you know that x only ranges till 1. So that this portion over here means student will take 1 hour. Okay, now in order to compute this I can write 1 minus L1. So this L1 means student will take less than 1 hour. So you know that given the probability that is x by 2, so this is 1 by 2. So now p of f is equal to 0.5. Have you understood this? Have you understood this?
Yes, sir.
Now if you understood this, now we can see this probability that f intersection L 0.75 complement. I can write it directly as p of f. Okay, so how can I write it like p of f? So because I am saying that intersection that student will take greater than 0.75, and here I am saying student will take full hour. So it means like it's like something like this. So this is f, this is 1 hour, and this is 0. And he is taking 0.75 complement. That is what is outside this. So this is he'll take less than 1 hour. So if he takes less than if we take complement of this, the complement means he'll take greater than or equal to 0.75. So that will belong to this. That belong to whole of the 1 hour. So then this becomes like this. So here if I have to compute probability of f given L, I think 0.75 complement, so this will be equal to probability of f given intersection of L 0.75 C divided by probability of L 0.75 C. So this will be p of f. That's why I computed p of f divided by this will be 1 minus probability of L 0.75. L 0.75. Now you know p of f is 0.5 that we computed, divided by 1 minus p of 0.75, because L of x is equal to x by 2. So he can write it 0.75 divided by 2. So this comes out to be 0.5 divided by 1 minus 0, that's 2. This is 0.625. This is equal to 0.8. A little bit tedious question, but I hope that you understood this. How many of you understood this?
Sir, how is the intersection of full hour and the complement of L 0.75?
Have you understood this? Did you understand this? What is the meaning of L x complement? the first thing is I'd give you the, like, for example, think about this, because think about the whole discussion will again go on this. So I'll have to make you understand this. Please and please watch the recording again if you're not able to understand this. In the next class, we'll first discuss how did I arrive at this. But first, try to understand what did I mean by this L of x, what did I mean by L of Lx complement, and then you will be able to arrive at this. Okay, and now let's get to the second problem, which will be a little bit easy, so that you are able to understand. The problem goes like this. This question is, you are flipping a coin twice. Okay, you are flipping coin twice. So you know the sample space of the coin will be head comma head, head comma tail, tail comma head, tail comma tail. So these are four possible outcomes in the sample space. Now, what is the conditional probability that both flips land on head? Given what our question is, so this is our sample space. Question is, what is the conditional probability? Conditional probability that both flips land at on heads. Both flips should land on. Given the first thing, A part given is that the first flip was heads. The part B of this is at least one flip is head. At least one flip is head. This is the question. Again, explaining you, this is, we are flipping two coins. You know that this is the possible outcome. Now you have to find two things. The first thing is, tell me what is the probability that both flips will be head if the first flip was head. And second thing is, what is the conditional probability that both flips will be head if one of them is head. So this is what you have to compute. So here it is. The event B, I said that this is probability that both flips land on head. This is both land on head. So this is the first flip land on heads. So this is probability of B given F. So I can write a probability of B intersection F divided by probability of F. So what is the intersection in these? How many elements are there in here? So probability both the flips are head. That's only one. Okay, divided by how many are the flips in which there is two heads? The first flip is head, so this can be head, tail, and head. So there are two events like that. So this is 2 1 by 2. Okay, now again you can say for the second part B, I just erase this out. Part B is probability of B given, let's call it A. So now A is the event in which at least one of the flip was head. Okay, so again here we will have probability of B given A is probability of B intersection A divided by probability of A. This is equal to the probability for B intersection it was 1 by 4. Okay, and probability of A given was 3 by 4. This is equal to 1 by 3. Okay, Zakir, did you do the question the same way?
Yes, sir.
Yeah, you again see the recording, because I think we'll still continue this conditional probability in next session, and you just watch this recording once, and then we'll go through some more questions so you understand it properly. So I'll stop the